Good afternoon. Thank you for the Institute for inviting me here, for spending this wonderful 7 weeks here working, actually coming here with this idea that this what I'm going to present today should work, and then really working it out. Sorry. So what I'm going to tell you today is really the result of a paper that we published last year, and where we modeled the transition to another new nematic phase with Q-tensor approach. And then I realized that this can be also used not only for modeling this new splay nematic phase as we think it is, but also the twist bend phase that was discovered some years earlier. So, and in this work, since this is a week dedicated to women researchers, I should really point out that a lot of this work, most of this work, was carried out by my old colleague and ex-student Alenka Mertelj. Where's the pointer? Now, what do we do? Sorry. And then Nerea Sebastian, she's a wonderful woman who came to us as a Marie Curie fellow and is now staying with us. Hopefully she gets some more permanent financing also, but this is a thing that's very difficult with us. And the material that we found this new phase in was made by Richard Mandel from York, from also the group of John Goodby. So I'll first explain a little bit about the two twist bend and this new splay nematic phase. Then I will go to quickly go over the description of elastic response of a nematic in terms of Q-tensor, since this is the basis of our model. Then I will show some experimental data on temperature dependence and order parameter dependence of elastic constants in both cases, which because one of the defining features of both phases is that some nematic elastic constant in the upper phase is soft, so sort of becomes this defines the type of instability that we expect. And then I will present this small model, which is coupled with flexoelectric polarization that is able to describe all these nematic modulated phases just by changing the value of a single parameter. So now let me first remind you of this very beautiful helically twisting periodic phase that happens in flexible dimers of usual nematic or several usual nematic compounds. This was actually first theoretically proposed by Ivan Dozov some 17 years ago, who realized that if in that case, if bend elastic constant goes to 0, then there must be some modulation in the system. And he found out that one possible, the most probable state actually is this helically twisting nematic phase. And then we experimentally was found in this soft flexible dimer that bend elastic constant is always decreasing towards the transition. It doesn't go really to 0, but is characteristically decreasing. And we made some measurement in these early experiments by light scattering, which I will present later on, and then also freeze fracture experiments, and then later also X-ray experiments, resonant X-ray experiments, confirmed that there is a periodicity in these phases, and it's in the nanometer range. So the structures that were proposed by Ivan Doza were actually two possible ways of accommodating spontaneous bend in the system. One is the twist bend on the right, where you have molecules going around a helical axis with primary bend, but also some twist in it. And then there is another planar deformation, which is primarily bend, with also some additional small second order, one should say, in higher order in this theta deviation angle splay. Now, so we recently also, last year, found, we are really lucky that we sort of, with Richard Mandel, he sent us this new material that showed some strange transition, and then we looked at the elastic constant by light scattering and found a very nice softening of the elastic constant, which shows that there must be, of the splay elastic constant, which shows that the splay must be present in the low temperature phase. Again, the only way to accommodate a splay in a large system is by periodic splay modulation, and this is how we so the molecules is like this. It's not really obviously conical in shape, which one would expect for a splayed molecules, but it is bulkier on one end, and on the additionally it has a large of 11 dBs electric dipole moment, more or less along the axis of the molecule. So when you look at the transition, there is really very little that happens. You have, but so across the transition, you still retain the typical Schlieren texture of the nematic phase, but with obvious changes in the fine changes, like this. Sorry, I can't find the. No.
The lens, it's the top one. Yeah, it's the top one.
Sorry, I don't have my glasses on. I found it. So this is the normal nematic phase, and this is now this new low temperature phase, and there are some easily visible domain boundaries with slightly different birefringence. Now we interpret this, that this what happens in the low temperature phase is that we get spontaneous splay modulation with the modulation vector perpendicular to the nematic director. Now you expect this kind of a phase on if the period is much smaller than the wavelength of light to be biaxial, but this is not the local biaxiality, is the sort of a coarse-grained biaxiality, which will bring about a different response for different orientations of the secondary optic axis, of the secondary axis of the dielectric tensor. So now let me, maybe I should also point out that we this phase, due to expected flexoelectricity since you have one direction of splay this in this domain and the other direction of splay in this domain, you also get opposite directions of flexoelectric polarization. So this is also in this model an anti-ferroelectric phase, which should show strong dielectric response, and we are looking for it, and we are finding additional strong features in the dielectric spectrum at low frequencies. But unfortunately, this material has lots of ions in, and it's really difficult then to separate the true dielectric response from the simple ions which nearly swamp nearly everything. So I don't present any of this data. So now let me say a little bit about nematic elasticity. This is well known, of course. The usual description of nematic liquid crystals in terms of the Q-tensor. This is, of course, a traceless second-order tensor. You have the Landau terms that describe the transition, with the A term being the one that is temperature dependence. And then there are usually added two elastic coefficients in the gradients of the Q-tensor. These are actually the only two terms. There is another term, but which can be expressed as a divergence plus a linear combination is two ones. These are the only two relevant terms for the bulk. But now, if you look at the other way of describing elasticity in nematic, of course, this is the Frank-Ossen description, which has three elastic constants. And if you map now the bend and splay term to the Q-tensor expression, you find out that the bend and splay elastic constant have the same relation to the Landau elastic term, so they are degenerate in this description. And I will, if I have time at the end, make a little bit more comment on this at the end. So one has to look for additional terms in the expansion in Q-tensor, and it's well known that if you add so-called cubic terms, so the quadratic ingredient, but with another term, with multiplied by the Q-tensor itself, then you break this degeneracy, and there are actually 5 such terms. I only wrote 3 because that's more than enough for what we need now. So now the usual bend, twist, and splay elastic constants are related to this Landau expansion elastic coefficients in the following way. So you see that the first two invariants in cubic invariants both break the splay and bend degeneracy in a sort of opposite way, so it actually doesn't really matter which term you use to break the degeneracy. Now let me show a little experimental these are elastic constants of first of the twist bend nematic phase. These are our measurements of a mixture that was published in 2013 with the people from Southampton, and we measure this elastic constant by light scattering. This is essentially you look at the intensity of scattering plus at the relaxation rate of the fluctuations, and you can get both viscosities and the elastic constant this way. And especially in this mixture, which is close, where the transition is close to second order, actually it goes in this particular mixture, one can actually find the critical point where transition is exactly second order. The bend elastic constant decreases quite dramatically as you go towards transition. While the other two, the twist and splay elastic constant do not, more or less not much to the transition, and interestingly the splay elastic constant increases quite strongly below the transition. This has been explained very nicely in a paper published by the Kent group, also doing light scattering, doing coarse gaining across this period of this twist bend phase. So we can also measure the birefringence in this system, and this is proportional to the order parameter. And so look for this bend elastic constant in a pure system. This is CB9 CB. This is a biphenyl with 9 carbon atoms, flexible chain in between, and it also shows the same kind of decrease in as a function of temperature. But we can plot this now, the elastic constant, not as a function of temperature, but as a elastic constant divided by the optic anisotropy squared as a function of optic anisotropy. The linear dependence gives out the cubic part of the contribution to the elastic constant, and we see that the band elastic constant is actually driven to low value essentially by the decrease of the order as the order parameter is increasing. So it really shows that the importance of the separation of the band elastic constant into the quadratic part and cubic part, and the same for 7 CB and 9 CB. So now let me say a little bit about this new splay nematic phase. Here the elastic constant of above the transition to display state is the one that is very nicely soft, is the splay elastic constant. The band elastic constant does nothing. Twist elastic constant, this is probably experimental, this is not real, and we have two ways of analyzing this data. So one way of analyzing, more crude one, gives this kind of decrease. If we do some additional assumptions, we actually think that the actual elastic constant goes to a very, very low value before the transition. And now I also show here the birefringence measurement, which shows that in this particular case the order parameter and birefringence don't change much across as you approach the transition. There is a small decrease below the transition, at the transition, which actually allows us to calculate what is the approximate tilt angle in the splayed phase due to the decrease of which decreases the effective optical anisotropy, the main part of the optical anisotropy. So now let me say a little bit about the model. So the Dozo model, the one that Dozo from which theoretically proposed this twist bend phase, was actually assumed. He actually simply assumed that the bend elastic constant decreases, goes linearly to 0 at some temperature, and then assumed some higher order terms in the elastic response, which I don't really like because they involve higher order derivatives, and as you know, this is not very nice as far as the variational calculus is concerned. So, and he then gets that this splay twist bend phase is stable for small enough splay elastic twist elastic constant, and for too large twist elastic constant, the splay bend phase is stable. And now in 2013, Shamit and Jonathan Selinger proposed a model which is actually based on an observation by Robert Meyer from many years ago, that flexoelectric coupling of nematic deformation and polarization can actually lead to some kind of instabilities. And now if you take this idea and actually they put down this kind of free energy, elastic free energy, where with the usual terms, splay, twist, and bend, and then polarization term plus flexoelectric coupling term plus additional terms which are needed to stabilize the deformed phase. Now, in all this, there is a similar approach was also taken by Lech Longa very recently, where he looked for the Q-tensor expansion, including flexoelectric coupling, but not including this cubic invariance in the elastic energy. And he actually then very nicely parameterized the Q-tensor in terms of the spherical tensor components, so looks at all possible phases arising from this flexoelectric coupling and quadratic terms in the gradients of the Q-tensor. And now the result of this model is that, yes, indeed, if you assume that this constant before the polarization has some linear temperature dependence, then you see that the effective bend elastic constant can go to 0 at a certain temperature, and also you can see what's happening to the effective flexoelectric coefficient and so on. I should also comment that this polarization term does not need to be really an actual electric polarization. It can be some kind of a shape thing. You can think of, if you have, for example, a bend shape, this will show up in the octopolar moment of the shape of the molecule, and now you can contract that, and then you get a vector which you can couple to bend. Now, the unified model that I want to present now is actually based on this observation that in the twist bend phase, we see that the higher order contribution from we see from the elastic constant dependence on the order parameter, that the cubic contribution must be important in some way. So here we wrote down the simplest expression in elastic free energy that is sufficient to describe not only the twist bend or the splay bend, the dorsal splay bend phase, but also this new phase that is most periodically modulated splayed phase. The first two terms are the quadratic terms in the I forgot another, just a square missing here. So the two quadratic terms in the elastic free energy, where I have transferred the dependence on the nematic order parameter from the Q-tensor to the C1 and C2 and B constant, and then we have this important cubic term where I will show that just assuming what is the signature of this B term gives us either twist bend or splay phase, and then we have the important flexoelectric polarization coupling term plus this term which with T, like in the Schmidt model, we can take to be temperature dependence, but I will show that it's not even necessary. And then we need the stabilizing term, and this is the lowest order stabilizing term that you can write so this is then sufficient to describe it. So now for the twist bend case, I assume that the B constant is negative because with the invariant that I have used, the bend elastic constant is expressed this way. So if B is negative, that means that this will decrease the bend elastic constant. Then, since we expect the phase to be the twist bend modulated phase, I take the parameter. You have to choose some kind of parameterization for the Q-tensor, and this is the easiest way to parameterize it. So then you take the nematic order director to describe the twist bend phase, put it into the Q-tensor, and then assume. You don't have to assume anything about the polarization. You put the polarization in the free energy, then look for Euler-Lagrange equations, so the variation of the free of the energy with respect to the polarization. You get the Euler-Lagrange equation. The only solution compatible with this assumption for the Q-tensor gives you that the polarization should essentially be perpendicular to the axis of the helix and to twist around like you expect. Now you plug that in back to the free energy and expand it to the fourth order in the angle in the bend angle, or you can actually just put in the sine theta and it's the same expression, but we have to look for small deformation anyway if we want to get through algebra. So then you get an expression like this for this reduced free energy with this bare bend elastic constant being these two quadratic invariants plus or minus the absolute value of the cubic invariant. And when you look for stability, you see that you get the effective bend elastic constant becomes 0, and this with essentially the same expression as in the Schmidt model. Now, with the TC given again by this simple expression, and I have to say that now it doesn't really matter whether this is a constant and this is decreasing with temperature, or is T going towards 0 with at some point. In both cases we can get an instability. So I just remind you that in this particular case of these flexible dimers, this bend elastic constant strongly depends on the third power of order parameter. Now below the transition point you have to solve the equations for stability, for the equilibrium in terms of this angle theta and in terms of the modulation wave vector. It's quite messy, but fortunately by going to the lowest order in the temperature below the transition temperature, it can be actually reduced to this very simple expression, and also the wave number governing the modulation is also governed by this extremely simple expression. So one can also look for this other possible modulation for planar bend with some splay, and put this. So then you have to take as an ansatz to the director something like this. Put it again into the Q-tensor, expand the elastic free energy to fourth order in the theta angle. Again, calculate the polarization dependence, and now we have polarization which is partly in the mostly in the x direction, and to some higher order in some part of it in the z direction. Again, plug that back into the free energy. For as far as the above the transition is concerned, is the same as before. And below the transition, you see that to the lowest order again in the temperature below the transition, you can get a closed expression like this, with again the same modulation period. Now you can actually ask which is the more stable phase, the twist bend or the splay bend. So you have to put everything back into the free energy look, which is then small, which gives you a smaller number, and you come up with a condition that the twist bend phase will be stable if the twist elastic constant is smaller than 1/2 of the average value of the bend and splay. And this is of course something that will in most cases be satisfied. So this is why we are only finding the twist bend phase and not this other splay bend. It's also the twist bend is much nicer since it has chiral symmetry breaking. Now if you can also see the same how it works in the case of this splay, this new splay phase. Now we just change the d parameter in the elastic free energy, take it positive instead of negative. Now take the ansatz for the director to be splay with the wave vector perpendicular to the nematic, to the original nematic director. Again, put it in the Q-tensor, expand the elastic energy to the fourth order in theta, and again calculate the polarization from the Euler-Lagrange equations, put it back into the free energy, look for stability, and then of course now the splay elastic constant becomes soft at a temperature which, or at this value of the parameter t, while this is the sort of bare splay elastic constant, that would be elastic constant for splay far above the transition. Again, we can then look also at the what is the structure below the transition temperature, and it's again messy, but you by expanding to the lowest order in temperature, again you get these simple expressions with polarization. Main component of polarization just pointing upwards or downwards, depending again periodically. So we have a periodically modulated polarization. It means an anti-ferroelectric state. Now I should probably just point out that these are all these minima are really minima. I have checked that by plugging everything in to free energy, expanding to second derivatives, and it's possible to analytically see that Hessian is in all cases positive definite. So it is they are all minima. So I think I could stop at this point. So we can show that we have two kinds of phases modulated now, either modulated perpendicular along the director. This is this twist bend phase, but there is also possibility for the splay modulation perpendicular to the nematic director, and both phases, on all these phases, can be modeled by free energy with cubic invariance, just in flexoelectric coupling that describes all these phases. Now, since I have 3 minutes left, maybe we should. No, let me just show something. Okay, this is just another page. Doing this work, I was actually struck by something that may be very naive. Maybe everybody knows that. I didn't know it, so this is how I'm going to show it anyway. The general elastic expansion in terms of gradients of Q-tensor should look something like this. There has to be some sixth order, sixth rank tensor that makes this bilinear form, and the reason why I'm saying this is that for some people, for example, Trebin and Longa have claimed some time ago that, and they actually consider that this is true, that formally the cubic invariants are not positive definite. It's not probably a very big problem because the size of the Q-tensor is limited anyway. But if you write the formal expression like this, and if you choose these coefficients in a proper way, then this is manifestly positive definite. Now, this sixth order tensor can actually be expressed first with some isotropic components, which are actually the important ones, the ones that are entering the Landau-Degeneracy expansion, but then you can add terms which are proportional to the undeformed Q-tensor times some fourth order isotropic components, and perhaps some other terms I haven't even called. This actually exhausts all these 5 additional invariants that are known in the cubic expansion. This 3 plus some others. Now, but this has to be the undeformed, locally at least undeformed, uniaxial tensor, and then there is even formally no problems with positive definiteness. So properly one should really write the elastic free energy with these Landau terms plus cubic terms, but which are not really cubic. They are actually quadratic in gradients and multiplied by locally undeformed Q-tensor. And in practice you can ensure this local condition by just saying it has to be formed as a as a uniaxial tensor, that means as a simple Cartesian product of the director. Thank you.
Any question? First one.
So remind me what the experimental situation with the measurement of K is.
Which one? K display.
The inverse wavelength of the modulation.
Yeah. No, I should comment that for this new splay phase we don't know, and we have experiments. As I say, we have experiments in dielectric constant which show that it may be anti-ferroelectric, but we can't really be sure. We have tried to do X-ray scattering, but we see nothing. Now, on the other hand, with twist bend phase, the modulation is 7 CB and 9 CB. It's about 8 or 9 nanometers. So it's way sub length.
Much shorter wavelength.
Yeah. And
would be consistent with the square root of delta t that you have there.
Yeah. Well, actually, I should perhaps also comment on this. Of course, all these models assume second-order transition. The actual transition is first order, but you can actually put that into model by adding higher order terms, of course.
And the question at the back, maybe?
So I had a question about the flexoelectricity. So the way you treated the flexoelectricity was using the polarization as an extra order parameter, right? And that couples somehow to maybe to the Q-tensor. Well, in for example, how Meyer did it is that he expresses the polarization in terms of gradients of the Q-tensor and let it couple to, for example, an electric field. So what's the physical difference between that treatment and using, for example, P as an extra order parameter?
But no, I'm not sure that I quite understand. I mean, flexoelectric coupling is coupling. The usual way of saying, of presenting is coupling, of course, of the director gradient of the director deformation of, let's say, either splay or bend to polarization. They are formally vectors, so you can actually just make a dot product with polarization and you get a scalar which you put into the free energy. Now, but this is essentially the same. You have a vector and the divergence of the Q-tensor, which, so again, you have, if you write it out, it's the same terms. Now, maybe there is a comment, again, necessary. In this language, you only get one flexoelectric constant, and you know that there should be two. Now, the higher, so the two constant you can get by again inserting another Q0 tensor in here, and then you get the splitting of the two flexoelectric coefficients.
I need to say that in the simplest way of seeing it, that you can write Pi as Qij, comma j, and that, but with some coefficient, and that couples to, for example, the gradient of the electrostatic potential.
Yeah, sure. But this is then additional terms that you put in here.
So without treating P as an extra order parameter field.
Well, this is the question: what you call the primary parameter or secondary parameter in the Landau description. There is no. There is no spontaneous polarization in the high phase here. This polarization that appears in the low temperature phase is simply the result of the coupling, and so there's no difference.
So I have a question. So how do you claim that B is maybe negative for twist bend or positive for display? Is this something that works, or is there a physical reasoning or experimental evidence?
Well, it's just in the case of the twist bend phase, there is also experimental evidence. Yes, actually, which term you take here? I took this first term, and then you have to say that B is negative for the twist bend and positive for the display phase. If you take the second term, you should just simply switch the signs, or you can take any combination of the two terms, and then you can actually play with what is the size of the splitting of the bend and twist bend and splay elastic constant.
And is the background field always uniaxial?
Yes. Yes.
That can be experimentally checked.
Well, it's very difficult to check for biaxiality.
Any other questions? If not, let's thank Professor Copic.